Welcome to the first main topic of computer network security, which is network security. Like I said I would do, in the first slide, I provide a bunch of links to some of the topics that we discuss in the remainder of this set of lectures. As you can see, we're going to talk about scaling techniques, ARP, LibNet, TCP dump, session hijacking, Kaminsky's trick, and so on, and a bunch of other things. And at least at the time of writing, at the time of recording, these links were actually active. Now, verify that they are. If not, you can find this material elsewhere also. It's not the only source of information, right? So these links are some examples, but you will see that in the presentation itself, on the slides, there will be additional URLs that you can use as background information. Okay, so let's dive into the details of network security. What we're going to do is look at typical network protocols, just like the ones that you've had in computer networks. We're going to look at TCP/IP. We're going to look at Ethernet and the address resolution protocol, and then we're going to look at attacks that you can do with that. For instance, sniffing or spoofing, okay, or fragmentation attacks. We're going to look at transport layer protocols such as UDP and how you can do scans and hijacking there. We're going to look at TCP and look at scans, spoofs, and hijacks there. We're going to look at the Internet Control Message Protocol, ICMP, and briefly, for historic reasons, look at Smurf attacks and more modern variants of the Smurf. And we're going to look at IPv6, IPsec, briefly, and wireless local area networks. And finally, we're going to look at a number of internet applications such as DNS, FTP, perhaps, and some others. Now, the things that we're going to talk about are the typical network protocols and network layers that you've had in computer networks. And just as a recap, I want to remind everyone that in computer networks, we typically talk about the network protocol stack as 7 layers in the ISO-OZ reference model. But in practice, we typically talk about a physical layer, a link layer, a network layer, a transport layer, and an application layer. So the physical layer is maybe the copper wire or the radio signals that you use to transmit your data. Okay, and at the link layer, we find part of the implementation of the hardware, right? So part of the hardware interface is in the link layer. So for Ethernet, for instance, and we find a number of other protocols there also. And one particular protocol that we're going to be looking at is the address resolution protocol, or ARP. Okay. Above the link layer, we find the network layer, and the network layer, the most important protocol is the IP protocol. Okay. IP protocol is the protocol that is responsible for routing your traffic from one machine to another machine far away on the internet, and for a number of other things also. It's not the only protocol that we find at the network layer, but it's the most important one. Another protocol that we're going to be looking at is the control message protocol, right? So the protocol that's, for instance, is used when you send ping, right? So an echo request, and then you wait for an echo reply, and also that is sent when something goes wrong. For instance, if your packet cannot reach its destination, the router may send back an error message over ICMP. Okay. We're not going to look at other protocols in the network layer. For instance, the group management protocol, not something that we're going to be looking at. Not that important either. Above the network layer, we find the transport layer, and there are essentially only 2 protocols that really matter. It's UDP, which is a really bare bones, no frills network protocol. Hardly any more interesting than IP and what it offers. And then there is a super complicated TCP protocol, which offers in order, reliable connections, and a bunch of other things. Okay. Above the transport layer, finally, we have the application layer, and here we find the interface to the actual applications, right? So the protocols that we see there are things like HTTP for the web, or DNS for name resolution, and so on. Okay. So those are the things that we're going to be looking at, and we're going to focus on the protocols that we actually use a lot. And we're going to start simple, right? And the simplest kind of attack is the attack where the attacker is present on the local area network. So it's directly on the segment that the victim is also present at. And we're going to look at typical things that are at least parts of attacks, such as sniffing, spoofing, hijacking, and ARP attacks here. And the goals for the attacker are quite diverse, but typically what the attacker wants to do is impersonate a host, maybe to circumvent some security mechanism. For instance, maybe only particular hosts are able to access certain servers. The attacker may want to deny service, so denial of service attack, may want to get access to confidential information, or it may want to tamper with the delivery mechanism. And let's start with the potentially one of the simplest things that you can do, and that is sniffing, right? So you just want to read data from other people's network traffic. And this is a stepping stone in many other attacks, more advanced attacks. Okay? And in theory, at least, it's extremely simple. What you can do is simply set your network card to promiscuous mode, and then you suck up all the data that comes whizzing by on the network. Okay? Certainly in the wireless domain or in old school Ethernet, all the traffic is sent on a broadcast medium, so you only need to set your network card in promiscuous mode, and you will actually receive everything. Okay, that's great. And you want to do this because even today, when encryption has become much more popular and is getting more popular by the day, there's still a lot of network traffic, a lot of protocols that send data in the clear. So some old-fashioned protocols such as FTP or post office protocol, but also HTTP, for instance, by default sends its data in the clear. And if you look at this data, you'll actually receive this confidential information. For instance, this could be usernames and passwords, files, mail, etc. And there are many tools available to help you with that. For instance, if you install the dsniff package, you get a whole score of tools, such as dsniff itself, but also file snarf, mail snarf, message snarf, URL snarf, web spy, for reading data that is in the network traffic. It also contains a number of other tools. For instance, for spoofing, it has ARP spoof, DNS spoof, and MACOF to help sniffing. Right. So some of the spoofing is required to help sniffing, and we'll see examples of that in a bit. And finally, it has a number of tools for man-in-the-middle attack. So there's an SSH man-in-the-middle attack tool, and there's a web man-in-the-middle attack tool. And we'll see examples of how to do man-in-the-middle attacks later without these tools. So we're not going to focus on the tools, but how do these tools really work? Besides the ability to do sniffing, it's also good to know how to detect that there are sniffers in your network. Well, sniffers are typically passive programs, so they don't do much. And that means that you cannot easily measure things because there's not a lot to measure. Now, what you can do, of course, is go to all the machines, assuming that you can, that are connected to your local area network, and simply look at their network cards. And if they're in promiscuous mode, it's very likely that there is a sniffer in your network. Okay. You can do this by means of the ifconfig command on Linux, for instance, or CPM, check promiscuous mode. And here you see that ETH0 is indeed in promiscuous mode on this machine. Now, unfortunately, this is problematic for two reasons. First of all, you may have kernel-level rootkit. So a kernel-level rootkit hides the traces of something being out of the ordinary, right? So it might just, if you type ifconfig, it might just return that it's not running in promiscuous mode, even though it is. The other problem is that you may not have access to all the machines that connect to your network. So what else can we do? Well, there's a number of other tricks that we could use. We can also look for suspicious DNS lookups. Often sniffers, so people who are interested in obtaining your traffic, will filter out the interesting traffic. Okay? So maybe they're only interested in all the traffic that goes to a particular website. Now, what they see on the network is IP packets that go to a particular IP address. So what they do first is a DNS lookup for that IP address to see if it actually maps to, so reverse DNS lookup, to see if it maps to an interesting server, and only dump the traffic if this is the case. Okay. That means that we can detect these DNS lookups. And one trap that you could lay for the attacker, for the sniffer, is to send traffic from a fake IP address, okay, something that doesn't exist in the local network, and then see if anybody's trying to resolve that IP address, because that would indicate that something is wrong. Another thing that we could do is use latency. So the assumption that we make here is that the NIC, the network card, is in promiscuous mode and needs to process every single packet. So what we could do is send an echo request, so ping message, to some host A, right, and measure how long that takes. And then we may generate a huge amount of traffic to other hosts, and then while we're generating that huge amount of traffic, measure again the latency to host A. And if all of the traffic needs to be processed, this will be slower. So in that case, the response time will be slow, and that is an indication that there is a sniff. Finally, what we could do in some cases is look at anomalous behavior that occurs whenever we try to do network processing when the card is in promiscuous mode. For instance, in some Linux kernels, a packet will be accepted even if it has the wrong Ethernet address, as long as it has the right destination address. And on some version of Windows, whenever the network card is in promiscuous mode, it will only, for broadcast packets, it will only look at the first byte. So these kind of things are also possible, perhaps, to detect sniffers. There are some tools, standard tools that you could use for this, just like there are standard tools for helping you sniff. There are also tools for helping you detect sniffers. The anti-sniff tool package is an example. Now, what if we want to sniff? Okay, what do we use for that? Well, we're not going to use very specialized tools. We just want to look at the basic principles, so the more basic techniques. And one of the most basic techniques, and very powerful, is TCP dump. Or, if you want to have something that is more graphical and does somewhat similar things, you can use Wireshark. But TCP dump is nice and convenient, and convenient enough, and extremely powerful. It's a tool that analyzes the traffic that is on the network segment. So you analyze it, and you can decide what to do with it. Maybe you want to capture part of the traffic, maybe all of the traffic. Who knows? Okay, it's based on libpcap, the packet capture library, and PCAP supports a very powerful expression language that allows you to identify exactly what kind of traffic you're interested in. Now, if you want to process and capture a lot of traffic from network cards, you actually need root privileges to use TCP dump. Okay, if you just want to, I don't know, process packets from a PCAP dump, you don't need that. But if you really want to sniff in earnest, you need root privileges to set your card in promiscuous mode. Okay. Now, I don't want to give you a detailed tutorial on TCP dump. In fact, I don't want to give you much of a tutorial on TCP dump at all. Just highlight some of the things that you can do. So we can cherry pick some of the command line options. For instance, you can print the link level addresses. If you use -E, you can decide that it shouldn't do a domain lookup to map the IP addresses to fully qualified domain names by -N. We can print the contents of a packet using -X. We can specify which network card we want to receive the traffic from with -I. We can dump the traffic in a file, in a dump file, using -W, and then read, so do the TCP dump on a file using -R. By default, TCP will actually dump only a small part of the network packets, 60 bytes by default. But with -s, the snap length, we can decide to make this, for instance, larger. Make sure that it will dump the entire IP packet. Okay, and like I said, we can use powerful expressions to determine which packets we want to receive, and normally we would specify these expressions on the command line. We can also write this in a file and then tell TCP that it should use that file for the expressions. Okay. Now, let's have a look at some components of these expressions. So all of the expressions consist of a number of primitives that consist of a qualifier and an identifier. And the qualifiers can be a type, a direction, and a protocol. Okay, so a type will basically tell you what kind of entity you're interested in. For instance, a host. In this case, we're interested in the traffic to and from the host Kuji, right? Or we're interested in the network to and from a particular, we're interested in the traffic to and from a particular network, or to and from a particular port. Now we can extend that with the direction. So maybe we're only interested in the traffic, again, not to and from the host Kuji, but only where the source is host Kuji. Okay, so it's in one particular direction. We can use source, destination, or we can use source and destination. And TCP actually provides these logical operators, as we shall see. Okay, and finally we can specify that's the last qualifier protocol. For instance, you can say that we're interested in the protocol Ethernet, and the source host should be this MAC address. Okay, so very powerful expressions. Okay, we're interested in the IP protocol, and it should be destination should be this network, okay, and so on. So now we can combine all of these with these simple expressions to make complex expressions with and or not and so on. And then it has a bunch of special keywords. So it has relational operators, less than, greater than, and so on, binary operators. It has logical and or and not, and it allows you to access specific bytes in a packet. For instance, for a protocol, you can have an expression for a particular byte offset. For instance, IP0. So if IP0, and then there's an AND operation with OXF. If that is not equal to 5, it basically means that your packet is a packet with options, right? So it doesn't have the 20 bytes. 5 times 4, it counts in multiples of 4 bytes. It doesn't have a 20 byte IP header, so it should be an IP packet with options. If you don't know the details of the first byte of an IP packet, so this doesn't mean anything to you. It's not all that important, right? So it just means that you can express that we're interested in looking at the first byte and then doing an AND operation with some value and then test it for a particular constant, and then we're only interested in that packet. Okay, kind of cool. So let's have a quick look at an example. In this particular case, we have. Oh, let me just make sure that you can actually see the example. Now you should be able to see the example. This is a virtual machine where I'm running very little at the moment, but it has a number of interfaces. So here we see that it contains a loopback interface, right? Just something that you typically use for testing purposes, right? And it has an actual interface, and the interface name is ENS33. Okay. So what we can try to do is dump the traffic. TCP dump on interface ENS 33. Now, this will fail because we don't have the appropriate permissions. We're trying to put this network card in promiscuous mode without, root privileges. So we can't do this. Now, if we do this with sudo, we'll see that it actually works, and we also see that there's a lot of network traffic in the background, right? So we actually get a lot of reports. Here we go. So we see that there's a timestamp at the beginning. It tells you a little bit about the protocol. It tells you about the source of the traffic. So in this case, it's coming from the gateway to Ubuntu. That's this machine. Let me just kill this because otherwise it's impossible. And it's coming from this IP address. It's going to that IP address. It's a UDP packet. It's a length 212. Okay. So a lot of stuff that we find in there, and if you want to know more about this, you should probably look at UDP in more detail. Now let's make this more interesting, because this is a lot of traffic, and we can't really process all that much traffic. Now, for instance, let's limit ourselves to, I don't know, web traffic. So we're only interested in the traffic with source or destination port 80. Okay, and we see there's nothing here. So there's no web traffic on this network card until we start up our browser, which takes a bit of time. And then we see there's actually a lot of network traffic whenever Firefox wakes up and starts doing some processing to obtain packets from new.nl, which is essentially a news source in the Netherlands. Okay, let's go back and see what it contains. As mentioned, there's an IP, there's a timestamp, there's the protocol, there's the source, there's the destination. It tells you about flags. If there's special flags in there, for instance, a fin flag or an urgent flag or things like that. It tells you about acknowledgements, there's the window sizes, and so on. There's a lot more that you can get out of this, and I don't want to go over the details. If you want to know, if you want to receive more, you can actually specify that it also should print out the contents of the data. Right now we actually see the content, and it only takes a small snapshot of the packet. If we want to receive the full thing, we can actually say that the snap length should be, I don't know, maybe you want to see the entire packet. Okay, then you receive the entire packet. You can write it to my dump file .pcap. Now it dumps it into a file, and so on. So you can construct your whatever filter is interesting to you. Great. So some other examples of what you can do with TCP dump are, for instance, TCP dump of everything that is on this network interface, ETH0, and we don't want to do a name lookup, and we want to dump the content of the traffic. Here we write all of the traffic that we receive, the full packet, so snap length 64K, into a traffic dump file. And what we're going to dump in there is all the traffic where the source is a host Hitchcock. Here we actually process that dump file as if we're doing just network sniffing, and we're looking for all the ARP traffic in the dump file. Here we look at a particular byte in an ARP packet. Here we look at the traffic where the source of destination is this gateway, and it's port 21 or port 20. So FTP related traffic. Now there's a ton of other things that you can do with TCP dump. It's very powerful, but I'll leave that up to you to study that yourselves. libpcap is what TCP dump is based on. It's a very powerful expression language. Study that also in your own time. By now, you will probably think, oh, wait a minute. So it all sounded very plausible when he said, wireless and old school Ethernet. But in reality, all the wired networks these days, wired Ethernet is switched, and that means that all the traffic that this host A here sends to host B there will go directly to host B and will never reach a link towards an attacker. That means that even if the attacker puts the network card in promiscuous mode, there's never any traffic from A to B on this particular link. So he's never going to see anything, or he or she. Okay, so how we're going to deal with that situation? How can we do sniffing in this situation? Now, what is going on when we say this is switched Ethernet? Well, this switch has a switch table, and the switch table records a mapping of port numbers and MAC addresses. Okay, and it's something that you don't have to configure. It will automatically construct this. You will probably remember this from your computer networks courses. So what the switch will do is it will see traffic that is sent by this host A here, and it will arrive on this port, say port 1, at the switch. So the switch at that particular moment knows that host A with this particular MAC address is on port 1, and it makes a recording of that in its switch table. Okay. Likewise, when it sees traffic coming from host B on port 2, it will record in its switch table that port B, host B with this particular MAC address is at port 2. Okay, so that is great for the switch, because next time there's any traffic sent from A to B, the switch knows where A is and the switch knows where B is. Okay, so it can directly send it onto this particular link. Okay. Now, what is the attacker going to do to still get to this traffic? Because the attacker needs that traffic. Well, there's essentially 3 solutions to that. And the first is MAC flooding. So remember, this switch has a switch table, and that switch table has only a finite capacity. So what we could do is go to a table that contains mappings from MAC address to port numbers. So what we can do is try and flood the table, right? So with bogus MAC addresses, we just send a lot of spoofed Ethernet frames with spoofed Ethernet addresses, and the switch will simply say, oh, here's another Ethernet frame on port 1 or port 2 or whatever for a particular MAC address, and let me make a recording of that, right? So then at some point this table is going to be full, and all the other traffic that is being sent will simply be broadcast, because the switch table is full. So if there's traffic for a MAC address that it doesn't know about, that is no longer in the switch table, it will simply send it out to all the outgoing ports. And then the switch essentially becomes an old-fashioned hub, a broadcast medium again. Okay. Another thing that you can do is, if the attacker knows the MAC address of the victim, the host that it wants to receive the data of, what it could do is impersonate it, right? So just do MAC duplicating or MAC cloning. So you send an Ethernet frame with a spoofed MAC address of that victim, and the switch is going to see that. For instance, here the attacker sends an Ethernet packet with a MAC address of host B here, right? The switch is going to say, hey, wait a minute, here's this MAC address on this particular link. Maybe this host has moved to another port. At any rate, what I'm going to do is record this new mapping, right? So now the MAC address of B is registered with this port, and that means that if host A here sends traffic to host B, it will now no longer be sent here, but it will be sent there. Okay, so that's MAC duplicating or MAC cloning. The final thing that you can do is so-called ARP spoofing, and maybe you can include forwarding and then construct a complete man in the middle. Now, what do we mean by ARP spoofing? Well, from your computer networks course, you probably remember that we need to do address resolution, and this is what we use the address resolution protocol for. We need address resolution because we may have a host here that wants to send a message to an IP address 192.168.1.10. Okay, they're all connected to the same switch, so it's all the same network segment. But this host does not know the MAC address of this particular host here. Okay. It only knows the IP address, right? This is at the higher level protocols. This is how we communicate. So how does it obtain the MAC address for this particular destination host? Well, what it will do is it will construct a message. It will construct, and so it has a message for 192.168.1.100, but it needs to find the MAC address, and to do that, it sends out an ARP request, an address resolution protocol request, and it contains the MAC address of the sender and a broadcast address for the destination, and it basically says, look, I'm interested in communicating with 192.168.1.10, and if this is you, please reply to 192.168.1.100. Okay. So let's get this straight. It has the IP address of the destination there, not the MAC address, because that's what we're looking for. It has the IP address of the sender, and it has the IP address, the MAC address of the sender. Okay, so this is being sent to a broadcast address, so that means that it will actually go out on all the links of the switch. Okay, so everybody receives it, but only one of them has this IP address, and only that host will reply. Okay, so it will reply with an ARP reply. And the ARP reply is very similar to the ARP request. It contains the MAC address of the sender. It ends with B8 here. It has the MAC address of the receiver, right? So this particular machine. So we don't have to broadcast this one. It can go straight there. Why? Because we know the MAC address of the receiver. We saw that before, and it basically says, I have this IP address 192.168.1.10, and it's at this MAC address. Okay, so now both parties know both the IP address and the MAC address for the remote side. Great, that's ARP as it should work. Now, what kind of attacks are possible on ARP? ARP is not a very secure protocol. It wasn't designed with security in mind. So, for instance, it doesn't provide any form of authentication. You cannot tell if an ARP request or ARP reply, if it actually came from the host that is set that is in the packet itself, right? So you cannot verify that this is actually coming from the site that is pretending to send it. Okay. So what you can do is, if you are an attacker, you receive one of these ARP requests, right? Because it was broadcast, you can reply, right? You can reply, even though you don't have that IP address that the ARP request is looking for, you can reply with your own MAC address, right? So, and if you're faster than the legitimate owner of that IP address, it basically means that all the traffic from the sender to that IP address will actually end up on your computer rather than legitimate. Okay, because these fake ARP queries, these fake ARP replies will poison the ARP cache at the sender side. You can also send fake ARP queries, right? If you can send fake ARP queries, you also poison the ARP cache of the receiving side. In both cases, the net effect is the same. You get redirection of traffic. So if the other side wants to send traffic to that IP address, it will actually send it to your MAC address, right? Rather than a legitimate MAC address. And you can use this for denial of service attacks and for man-in-the-middle attacks. So if you use it for denial of service attacks, you actually map the IP addresses to maybe a non-existing MAC address, right? And then all the traffic will disappear. Or if you want to do a man-in-the-middle attack, you basically make sure that all the traffic to all the IP addresses will go to your MAC address, and then you look at it and you make sure that afterwards you send it to the legitimate owners of the IP address. This is known as spoofing and man in the middle. Okay, so if we raise, this can be graphically illustrated as follows. So there's an ARP request coming from host A. The ARP request is broadcast to all the machines in the local area network, and here the attacker replies with a fake ARP reply. And if the fake ARP reply arrives at the host, the sender, before the legitimate ARP reply, this is the mapping that this machine will use. Okay. Now, unfortunately, at some point, the other host, so host B in this particular case, will also have sent an ARP reply, and this will also arrive at host A. And in that case, it restores the ARP to the legitimate value, to the correct value. That's not good for the attacker. However, since ARP is stateless, we don't even know whether an ARP reply that we receive was actually a reply to a legitimate request. So what we can do is simply send replies, right? So just send a fake reply, even if there never was any request, and that will also poison the ARP cache on the host A side. And just for completeness, I want to mention, and you probably remember this from your computer network course, is that the ARP cache has a certain timeout value. So a time to live value of maybe say 15 minutes or so. Okay, so for that long, the reply will actually poison the cache. So if you constantly send out, repeatedly send out these ARP replies, you constantly, even if this guy at some point also sends something, you will constantly repoison the ARP cache. So we can do this in many different ways, and we can use this for many different purposes. So we can use it to do a complete traffic redirection with a man-in-the-middle attack, in other words, by creating two interfaces with the IP addresses for the IP addresses of A and B on the attacker's machine. Okay, so we're going to have two interfaces. One of them that receives the traffic from A, and the other one for the traffic from B. And meanwhile, we disable the ARP functions on our own machine with an ifconfig -ARP. And then we set the ARP caches to the correct value using ARP dash and then a host and then some MAC address. And by now turning on forwarding, IP forwarding between the two interfaces, we have the situation that all the traffic will end up on our machine first. We can look at it, right? So we can sniff it, and then it gets routed to the correct, legitimate machine. In other words, the two communicating parties don't really notice anything out of the ordinary. All the traffic still arrives at its destination. Okay. To do this, we can actually use some standard tools, just like we had dsniff. We also have some companion tools there, such as ARP spoof, which allows you to redirect IP traffic using ARP spoofing. And we also have frag router, which allows you to do routing in user space. Now, great. So we can build a man-in-the-middle attack. If we want to change that a little bit, we can also do a man-in-the-middle attack somewhat differently by impersonating the gateway router and then making sure that we receive all the traffic to the external network and look at it and then send it on its merry way. Okay. And finally, what we can do instead of sniffing, so instead of obtaining the traffic as a man in the middle, we can also use it for denial of service by mapping it to some non-existing MAC address, and then all the traffic will fall on the floor. All right, so there's a bunch of tools. We can use these ARP spoof and frag router tools. We can also, if we want to do this ourselves, you look at the ARP cache or manipulate the ARP cache using the ARP tool. We can use ifconfig, and we can use ARP watch to look for IP packets. Now we want to do this ourselves. We don't want to use these separate tools. We want to build our own packets. And this is complicated. right? So you can easily send traffic on the internet using sockets, right? So UDP sockets or TCP sockets are what you get by default. But if you want to do something at the lowest level, right? So at the level of ARP or Ethernet in general, this is not so easy. For this, you need raw sockets, and that means you have to build this packet byte by byte, which is a very painstaking job. To make this easier, there are libraries to help you do so. And that's what we're going to be using. And we construct our own ARP packet. So we want to send this spoofed ARP packet to maybe an ARP reply to some victim site. So what we need to do is build up this low-level packet, which contains, it's essentially an Ethernet frame which contains an ARP reply. Right. And that means that all the bytes have to be correct. So it has to look like an Ethernet frame with 6 bytes destination address, a 6-byte source address. It has to have the right type. So OX8060 is the ARP request type, an ARP reply type. It has to have after the ARP content, it has some padding, and it has a cyclic redundancy check, just like a regular Ethernet. So you have to build this, and then you have to build the ARP request to reply itself, right? So, and the ARP request to reply contains of a hardware type, which is essentially an indication of which protocol at the link layer we're talking about. In this particular case, it will be Ethernet, right? So that's a hardware type. And Ethernet, if I remember correctly, was OX 0800 or I think so. And then it has whatever the value might be, but that's a hardware type, so it indicates Ethernet. And then there's a protocol type which indicates in this particular case IP, right? So Ethernet IP, and then the length of an address at the MAC layer, so the link layer address. In this particular case, it will be Ethernet, so it will be 6 bytes. And then the length of the higher level protocol address, in this particular case, if it's IPv4, it will be 4 bytes. So this illustrates that ARP is actually a versatile protocol, and it's not bound to Ethernet or IP. You can use it for any protocol to any protocol translation. Okay. Then there's an operation code, which basically tells you whether what kind of ARP message this is, and then it has the hardware address of the source, so your MAC address. It has the IP address of the source. It has the target hardware address if you know it, and it has the target IP address. Okay, so if you get an ARP reply, for instance, all of those 4 fields are known. If you send an ARP request, you don't know the hardware address of the target. Okay? And you actually set the Ethernet destination address to the broadcast address. Okay, so the challenge is to do this, to build this packet at a really low level, and it's byte for byte, right? So it's a lot of work, and you need to do this yourself. Now, fortunately, there's some help in the form of libraries such as LibNet. So LibNet is a platform-independent library that gives a number of APIs to help you build these arbitrary packets and then inject them at a particular network interface. Okay. In order to do so, you start with some initialization of the memory, some initialization of the network, and then you construct your packet and then inject it into the appropriate network interface, and then you do some cleaning, and then you're done. Let's see how we do this in our particular case for ARP spoofing. So our entire program consists of, I think, 2 pages, 2 slides. So it's not a lot of code. It's very minimal, and it constructs an entire ARP, a fake ARP reply. So start with some includes. Let's ignore those. And here we see the actual mapping. So there's a victim at 192.168.1.10, which has this MAC address. Then there's the attacker at 1.100, right, which has a MAC address that ends in A3. And finally, there's some spoofed host that lives at 1.30, and it ends with the MAC address ends at D1. So what the attacker wants to do is spoof that the IP address is actually at this MAC address. So that's what you want to tell the victim, so that the victim will eventually believe that that this IP address is at this MAC address rather than this MAC address. So to do so, we start by building some well, essentially the Ethernet addresses of the destination and the Ethernet address of the source. So Ethernet address of the destination is just an array of 6 bytes. Okay, and it's going to be sent to the victim. So it's that's the destination B8, and it's going to be sent by the source, right? And the source is the attacker, so it ends at 8. Then we do a little bit of initialization. So we initialize the libnet, and we basically say that we want to inject this at ETH0. So that's the network card that we're going to be using. Then we're constructing 2 IP addresses, a destination IP address. So that's the IP address that we are going to send our packet to, right? So we're going to send the packet to 192.168.1.10. And there's a spoofed IP address, which is the IP address that we're going to claim to have as an attacker, which is 192.168.1.30. Okay, so that's what we will send, and then we construct our ARP packet. And the ARP packet consists of a hardware type, which was Ethernet in this particular case, a protocol. Oh yes, so the IP protocol was 0800. And the length of the hardware address of the MAC address is 6 bytes. The length of the IPv4 address is 4 bytes. It indicates that it's an ARP reply, right? That's a type. And then we have all the addresses. So there's the Ethernet source address, which is the address of the attacker, the MAC address of the attacker. It has this spoofed IP address, which is the IP address of some other host. And it sends it to the MAC address of the target, the victim, and it sends it also to the IP address of the victim. Okay? And then we build this Ethernet frame, and we inject it into our network link. Okay, at ETH0, and then we're done. And what happens if we compile? Oh, important to note, there's been some confusion in the past about this. These characters that you see here are not ones, they're L's, right? So it's not a 1. Okay. So what happens if we do this? If we build this this program, we actually can do ARP spoof. And to illustrate that, here's what we see on the command line. We type at the victim side initially ARP-A. So inspect the contents of the ARP cache. We see that it has a mapping for 192.168.1.30 at this MAC address, right? The D1 MAC address. And that's a legitimate mapping. Actually the IP address is at that MAC address. Now, if we run our program, and at the attacker side, we run the send spoof ARP. That's what we called our program after compiling it. What we saw on the previous slide got compiled to send spoof ARP, and we run that. And what we see on the wire is that it actually sends out an Ethernet packet from A3 to B8 here, the MAC addresses, and it's an ARP reply, and it's telling the receiver, in this case the victim, that 192.168.1.30 is at this MAC address, which is the MAC address of the attacker. Okay, so that's what we've done. And then if we do this again, if we again inspect the ARP cache, we see that now it still has the mapping for 192.168.1.30, but it's at the attacker's MAC address. That means that if we start sending packets from the victim, so from 192.168.1.10, right? So this one, we ping 192.168.1.30, right? So this is a spoofed IP address. We see on the wire, if we do a TCP dump, that indeed there is a packet sent from our MAC address to the attacker's MAC address, and the attacker receives this ICMP echo request, even though it was not meant for the attacker at all. Now, this spoofing can also be done at different layers. So we can also spoof, for instance, at the IP level. So this is at the network layer. In this case, you impersonate a host by sending an IP datagram with the IP address of another host. Okay. And then if you're on the same local area network, you can sniff the traffic for the replies from the attacked host. Okay, so that's a powerful stepping stone, assuming that you have local area network access. Okay. Like sniffing, IP spoofing is a good stepping stone in many attacks. You can use it to impersonate sources of security critical information. For instance, maybe you can impersonate a DNS server or a network file system server. Or to exploit some address-based authentication, which is, by the way, a really bad way to authenticate. When some systems authenticate their users, so only allow certain accesses if the IP addresses are from the right sort. So if it's maybe they have a set of IP addresses that get certain accesses. Now, if so, you can impersonate those IP addresses and bypass the authentication. And just like in all the other cases, there are quite a few tools available to help you do this. But like we saw with the ARP spoofing attack, you can also construct these yourself. Combining sniffing and spoofing will get us to our first, hijacking attack, hijacking function. So it's still really simple. It becomes much more complicated when we move up in the protocol stack and go to more complicated protocols. But here we have a really simple hijacking example where an attacker waits for a client request, then races against the legitimate host to produce a reply. And if that reply actually arrives earlier, we have a hijack of the original interaction between the client and the server. Okay, now hijacking can be done at the ARP level. We already saw that where we race against the ARP request. It can be done at the IP level, where we do it with IP addresses. It can be done with UDP, and all those are still very simple. It becomes really complicated when we do it at a TCP level, and that's what we're going to look at in a later lecture.